Hi, everyone. I'm Jessica Valenciano. I'm a grad student at University of Notre Dame. And like Brad said, I'll be talking about crystal size distributions of the ilmenite in 73001. So this is probably something everyone's already seen a bunch of times, but Apollo 17 Station 3, the Taurus Littrow Valley on the southeastern border of the Mare Serenitatis, about 50 meters from Laura Crater. It's located on the light mantle landslide deposit, and here it is in contact with some of the trench soils that were also collected. So for this study, we used XCT scans, which there's an example of one right here, 73001, 1064A. So, so a really big benefit of using these XCT scans is that they allow for analyses without actually using a physical sample, because ilmenite is so easily identifiable in XCT, which you can see in these white phases. There's also some armalcolite rimmed by ilmenite over here in the corner. And all of the clasts that are in this study came from the first and second dissections of 73001, which I'll be calling pass 1 and pass 2 from now on. So here is another XCT scan of the entire drive tube 73002, along with clasts that have been analyzed in previous studies and their approximate location in the drive tube. And here is 73001, same thing, XCT scan of the entire drive tube, as well as the approximate locations of each class that was used in this study. And there are 14 clasts that were identified and crystal size distributions were conducted on. And you can see that there's a variety of textures here. And while the salt clasts were found throughout both cores, most of the clasts in 73001 were found in the central portion. So to introduce into crystal size distribution, here is an example of a crystal size distribution in 73001-261. So for each one between, in this study, between 300 and 1100 ilmenite crystals were traced. For some, depending on the amount of crystals available in each slice, several slices were used to gain enough crystals in order to do this, as there needs to be 250 or more in order for crystal size distributions to be statistically relevant. Any crystals that were on the edges or otherwise incomplete were not included because we don't know those boundaries, and we don't want data that's not correct. And then after these traces were made, they were filled with different colors, and if they intersected at all, they were traced on separate layers to avoid several crystals looking like one big crystal. So the areas of the crystals and the sample are calculated in image J and then put into then CSD slice determines the best shapes of these 2D traced crystals into 3D. And then CSD corrections is used to use the best fit ellipse and the major minor axis to translate this 2D to a 3D shape. And here is what the crystal size distribution profile looks like for the sample 73001-261. To introduce crystal size distributions a little bit more, they are a quantitative and non-destructive method, which can be, again, highlighted by the fact that these were able to be done with XCT scans and not actual physical samples. These quantify population densities of a given mineral phase, in this case, ilmenite, into set size bins representative of different crystal lengths. Then these are displayed on a log normal plot of population density against the crystal size, which shows the nucleation and growth histories of crystal populations. Here is an example of the kind of data and information that you can get from crystal size distributions. Here in red, we have a linear CSD, which linear and nonlinear are indicative of a constant cooling rate, whereas if you have different shifts in dynamics or kinematics or anything like that, you can get different profiles, such as concave up and concave down. There are also kinked profiles that you can sometimes get when you have a shift in cooling rate. So to go on to my results, here are the crystal size distribution profiles for the class found in 73001 pass 1 and 73001 pass 2. As you can see, the ones from pass 1 do have steeper slopes, with the steepest slope being here in pass 1 in the green. And then pass 2 has relatively more shallow crystal size distribution profiles, which indicates that relative to the steeper profiles, they cooled at a slower rate. And then here is, oh, forgot to mention, the y-axis is the population density, and the x-axis is the corrected crystal length. And moving on to the slope intercept plot, plotted the intercept on the y-axis against the slope on the x. And in the red circles is my previous work for 73002, and all of the diamonds are the samples that were used in this study. So something that I found interesting is that there are 3 different groupings that you can see, which both 73001 and 73002 fall into. And we have this fast cooling, this upper fast cooling limb and then the lower slow cooling limb. And just to make it a little bit easier to see, I've put 73002 in the red circles and 73001 in blue diamonds. So here is this upper limb or this upper grouping and the textures that were observed in these samples. And then we have the biggest group that contained 8 of the 14 class that were analyzed in here. And then we have this lower group that was much smaller. There were only 2 in this grouping. To reiterate, there were 3 distinct groupings that were seen. And this first grouping up here shows they're rare in previously studied Apollo 17 basalts and they're not often seen. So here from what we could see before, that, like I said, there are groupings that have both 73002 and 73001 samples in them. And here's just a comparison of the textures that you can see in these samples from the different drive tubes. And this is the one that was in that first grouping that was a little bit was higher. And then here's the second grouping that had the most amount of crystals. And you can see, like I had mentioned before, 1064A has some armalcolite rimmed by ilmenite, and there's also armalcolite visible in 51A. And then here's the last grouping where we have these textures. So for a discussion, plagioclase crystallinity is used to describe the difference between pohoihoi and flows. And we can see in this graph that these samples fall into either pohoihoi or lavalate, or rather lunar samples. And here's an inferred stratigraphy that shows, or rather, because of the lack of vesicularity in the samples, we can infer that the finer grained ones came from these upper layers, and coarser grained would possibly come from this sort of area in a flow. So in conclusion, to wrap it up, basalt class in 73001 display similar cooling rates to class analyzed from 73002. And again, they appeared to have 3 distinct groupings that are consistent with textural analyses that were done on 73002 basalt class. And because of this, I think this suggests that the class are all from the young light mantle deposit. Because they are so similar, they might not have pierced into the next layer. And but because crystal size distributions only determine, or rather tell cooling rate instead of chemical composition, whole rock analyses are still needed to determine if these samples fall into current basalt, Apollo 17 basalt classifications. And further on future work, we're currently exploring quantifying cooling rates using experimental charges. Here are some that we have already done using samples from Chenga 5. The top sample is Chenga 5 B001, which is the actual sample that was recovered. And the lower image is of the experimental charge that was done to compare cooling rates. Um, this one was cooled at 10 degrees Celsius per hour. And as you can see, the red is representing the actual Chang 5 sample with the yellow diamonds as the experimental charges. And they are mostly within error of each other. So we're very excited about that. And we're um, intending to try and do the same thing for these Apollo 17 samples. So thank you to the people at JSC. Thank you to Survey for the Schmitz, CERN, and Evans travel grant that allowed me to be here today. And thank you.